Welcome class. How was everybody's Wednesday? What? Good. Mine was good too. Anybody have anything to say? To me or the class?
I tried to show my friends how, well, there was this conversation came up over whether you would pick a certain $100,000 or a 50-50 chance at $1 million.
Okay.
And if I did the homework right, you're supposed to pick the $1 million because it has a higher expected utility, but none of them
Right.
were buying it.
Okay. So human beings don't necessarily accept utility theory. I agree. And now here's the question, are the human beings wrong? Well, it depends. If you were to have 1 billion of them, the ones that follow utility theory on average would turn out more wealthy than the ones that don't follow utility theory. So there's an argument to say they're wrong. On the other hand, maybe humans have actually got have 1 million years of evolution behind their decision-making processes, and maybe they, maybe actually not winning hurts more than zero. Maybe it's actually negative, and so they're approximating better utility. I don't know. But then if that's the case, couldn't we quantify that? Couldn't we actually assign a value to what they're doing and do it better?
It'd be more complex utility.
It'd be more complex. You'd have to basically get the preferences more correct. So what's kind of happening is I think humans are doing bad math to compensate for the fact that they have very complex priorities. Now, let's zoom forward 1 billion years into the future where we have strong AI. Humans are making decisions through their fuzzy brain, feely, touchy processes, and machines are making decisions through utility theory. They're calculating the optimal answers. Who's going to win? Well, this is assuming the machines have priorities that are as good as the humans. If they don't, the humans will still be better. Because utility theory is no better than the priorities used to use it. Another strong argument for utility theory is if your priorities, if you do something other than utility theory, no matter what your priorities are, you could be exploited by somebody else who uses utility theory. So that kind of suggests you probably ought to be using utility theory. Essentially, all of the arguments against it tend to fall down to you got to have more accurate priorities. So it's really just a tool. It's not all of AI itself. That's probably more talking about it than we need to do. Okay, cool. Did anybody go to the colloquium on Wednesday? So I really should have mentioned this, and I'm sorry I didn't. I stuck it on the calendar to remind myself to do it, and I put it on my list of things to say in class, and then I got distracted philosophizing about strong AI and taking over the world. And as that often happens to me, I forgot to tell you about it. So nobody saw it and showed up, right? Okay, well, bummer. I'm sure you missed out. I didn't go either because I had something I had to do at the time and couldn't get out of it. So. But every once in a while, we get these scholars out here to talk. One reason you might want to go to those is it's really hard to get scholars to give good presentations. I mean, we pay thousands of dollars to get them out here. And these are people from big-time universities that do good research. Presumably, there's not really anything greater than that in the realm of nerdy, scholarly communications. So it's a lot of times people don't attend these colloquiums because they say the guy's hard to understand or their English isn't very good or things like that. But there's a reason for that. These are the world-class researchers. If I could encourage you to usually attend the colloquia, in the long run you'll look back and you'll say that 3/4 of them were a waste of time. But when you actually get something out of it, it usually pays off big. So there's sort of utility theory there. Okay. Any grading issues with assignment 1? I think after last lecture, we're all set with assignment 1.
My grade still hasn't been posted. And
Okay.
the grader has said that I should have
So
a grade.
So he thinks he sent it to me?
Yeah, he sent me an email like an hour ago saying that my submission was fine. There's no grade posted.
If he has, I have not received the scores from him, so I guess I better go follow up with him and then I'll get back to you.
Okay.
In general, as soon as he sends the scores to me, I post them online.
All right.
I try to keep very little lag between there. So I'd like to say, take it up with him, but it sounds like it's my fault now, so I'll go find out where the latest scores are.
I'm not on the scores page.
You're not on the scores page. Okay, I need to add you.
Okay.
If you send me an email, that'll make sure I don't forget.
Okay.
Yes.
I don't have a grade either, but I was one of the people that the grader sent me saying, hey, it's wrong, and I emailed
Okay.
him back, and he actually made a mistake, and it was supposed to be right.
Okay.
Yeah.
I haven't received new numbers from him. As soon as I do, I'll post them. I need to talk to him and find out where the numbers are. So after today, if new numbers aren't posted. Actually, it'll probably take me till tomorrow. After tomorrow, if they're not posted, then start sending emails out to the grader and CC me. Okay? Okay. I'd like to start talking about assignment 2, if we may, because you guys have to do it and it's important you know how. So I made this Java starter kit. If you actually look at it, there's absolutely nothing in there. I think. It's a Hello World app. You should not need that. I don't know why I did that, so feel free to just write your own app. You don't actually have to use Java for this assignment. I'll accept it in whatever you want to get working on my server. Here's why I think you probably want to use Java. By the time we get to assignment 4, now the code I give you actually does come with a bunch of stuff. And if you want to translate that into your favorite language, that's great. Go ahead. And you can give it back to me and I'll post it for other future generations and that'll be good. I'm betting you want to do it in Java. And I'm betting you want to learn as little as possible because that seems to be the main thing students try to do in school. Therefore, you should try to do everything in Java. Okay? Okay. Obviously, I think that attitude stinks, but it's what I did when I was a student too, so what can I say? So assuming you go with Java, here's a bunch of code, and it's basically Java code that I gave you here, so I've done most of the assignment for you. But I want you to understand how it works, so let's talk about that.
So just to confirm, it's not academic dishonesty if it's on your webpage?
Yeah, I'll go with that. I will not prosecute. Okay. Let's suppose you are here. The letter S means start. You want to go there. The letter G means goal, something like that. And there happens to be a barricade here and there. Obviously, the optimal path is to go like that. Or is it to go like that? I don't know. Looking like it's probably that. Humans are insanely good at path planning in fuzzy land, but they're not very good at path planning down to the exact, precise, optimal path. So you guys look at this and you pretty much immediately know this is better than that, right? Sort of, using your human intellect. But now, how do we tell a computer that? How do you get from the start to the goal precisely? How do you find the optimal solution? We talked about it briefly. We're going to do breadth first search. Now, this is a continuous space rather than a discrete space. One way we could do that is we could break it down into blocks and then we could just do left, right, up, and down. Or we could do hexagonal squares or triangular ones if you're one of those gamer type people that likes hexagonal grids. How would you do breadth first search in a continuous space?
Integration?
You could integrate. That would give you the truly optimal solution. Yuck, I just don't want to do that. I wouldn't do that because that sounds horrible. Even though we have been doing it earlier, I think it starts getting nasty at large level. Suppose I do this. We start here. I'm gonna randomly pick a bunch of directions. Maybe I'll pick 8 directions, maybe 10. Maybe I'll uniformly distribute them around the space of 360 degrees. Suppose I can go to all of those locations. Now I'm going to start here. Now I can go there. I can go here. Go here. Go here. Go here. And go here. And this one can go there. And it 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 can go there. Please don't make me draw all the arrows. You get the point, right?
Wouldn't it be better to tell your algorithm not to backtrack on itself?
Yes, absolutely. In fact, that's my point I'm building up to. So, thanks for ruining it. No, that's actually a really good segue.
It kind of looked like you were backtracking.
I was on purpose to basically emphasize the dumbness of that. So, what's your favorite sorting algorithm? Bucket sort, insertion sort, merge sort, quick sort, one of those, right? If you're a parallel processing guy, it's Pythonic sort. So I have an electrical engineer for a father-in-law. His favorite sorting algorithm is order n factorial. Here's how the algorithm works. You take all the elements and you produce all possible lists by all possible orderings of the elements. Then you search through your set of orderings to find the one that's in sorted order. Because surely one of them's in sorted order, right? So this is an order n factorial search algorithm. It does work. You could, in fact, code it up. If your list is longer than, say, 10 elements long, it's going to swamp your computer and take all of eternity to finish. It's obviously a stupid sorting algorithm. That's why he likes it. What's wrong with this sorting algorithm? Well, yeah, it's slow. We can do better. Why do bad when you can do better? Unless you have a Turing machine, it stinks. Same thing for breadth first search. What's going to happen if I do this?
You're gonna get really tired of drawing.
I'm going to get really tired of drawing. My hand's going to get a cramp. But if you think about it for a minute, how many possible, from the starting point, how many possible locations are there? We'll say 6. Why did I pick 6?
6 arrows.
Because hexagonal grids. Do you know why snowflakes have 6 sides? This is a tangent, but I gotta do it. Okay. If you have a circle, I showed this to my kids the other day. They were really impressed. And another circle comes along and sticks to it. Doesn't really matter where it sticks. And you have another circle that comes along and sticks to it. Well, this circle can roll around that circle because it's only stuck in one spot, right? But as soon as you get right here, now it's stuck in 2 spots. Now it's kind of permanently stuck because you can't move once you're pinned in 2 positions. Along comes another little circle, sticks right there. And by circle, I mean little frozen droplet of water, probably. Well, this one can roll around. It's probably going to end up stuck like that, right? And another one comes along. Who knows where it sticks? Maybe there. Rolls around. It's eventually going to get stuck like that. You see what's going to happen? At some point, we're going to end up with makes a perfect hexagonal grid. Isn't that amazing? Why does that happen? Well, because if you go from the midpoints to them all, it makes a perfect equilateral triangle, and it always takes 6 equilateral triangles to make 360 degrees, because 360 divided by 60 is 6. And essentially, this is just self-assembly. If you've taken Dr. Pattitz's class, he teaches all about self-assembly and how snowflakes form and how you can use that to build DNA that does all kinds of weird funky things. So 6 sounds like a good number to me. If you're going to search outward in circular directions, I figure 6 is good. Okay.
Good question.
Yeah.
You were saying that this is a method to handle like infinite fields, or
Continuous fields?
Continuous, yeah, that's the word.
Well, what I'm doing right now is I'm discretizing. When this is all done, will the answer be optimal? No, because I didn't try all possible steps. If my step size is, as my step size approaches 0, and as the number of rotations I attempt approach infinity, this will approach the optimal solution by the time I'm done. In fact, I think I could just stick with 6.
Yeah.
As long as my step size goes to 0, it'll approach the optimal solution.
Do 4.
Could do 4. 4 will kind of do these sort of jaggy things.
But as it's 0, it doesn't, it's
Yeah,
rotation.
that's true. It depends how you add it all up. So if you do Manhattan distance, getting from here down like this is supposed to be exactly as long as going straight across and straight up. If you measure it that way, then no. If you fuzzify it and say that going like this is approximately the same as going like that, then yes. Then you're right, that will approach optimal. Anyway, this is great. You're thinking about it. That's all I really want you to do is think about it. So I'm making you think about it. Suppose I go out in 6 directions, and from each of those I go into 6 directions, and from each of those I go into 6 directions, and from each of those I go into 6 directions. How many steps do you think it takes me to get, say, from here to up there? 12? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nice answer. You're right. It was exactly 12. Okay, and in each of those I branch 6 times, and each of those branch 6 times. So the total amount of computation I'm going to have to do is, how do I do this? 12, 6 to the 12th power?
Yeah.
6 times 6 times, yeah, that's it. What is that, 2 trillion? And it's only 2 billion. Hey, that's that's doable. With only 2 billion computations, I can find the optimal path from here to there. And these step sizes are kind of big, right? Now imagine you're doing assignment 2. Can I assume you've already looked at the assignment, or do I need to introduce it to you? Who has not looked at it? No one's going to admit that. If you haven't, too bad. Okay, so we're doing it at the pixel level, and we're going from here to there. That's several hundred. 12 steps took us into the 2 billion range. What's several hundred going to take us into? I don't know, but crazy impossible. It's going to take your computer all of eternity to finish if you don't do something about that. So, fix my algorithm. What am I going to do?
Not backtrack.
Yeah, don't backtrack. Obviously, when I went up here and then going back down here, is there any possible way that's going to be optimal? No, because everyone knows the shortest distance between 2 points is a straight line. Point, point. Well, in this case, you can't go through the alligator pits, but we're still not going to go up and then back because that's just dumb. Obviously, we want to kind of go straight-ish, at least. So if we've already been there, don't go there again. In this case, we're in continuous space, so we're never going to land in exactly the same spot, unless we actually perfectly discretize our 6 positions. So how do we tell whether we've been there or not?
If the distance of your next point is less than, like, from your origin to your next point is less than the distance from your origin to the previous point.
That's a good solution. Yeah. So remember, we use these triangles for a reason, because it means we're kind of systematically chopping up our space. So what if we used a radius of a circle that's about equal to the, what would it be, the distance between the centers of the triangles, or half that, or double that, or something like that? Doesn't really even matter, as long as there's some radius of a circle around all of these endpoints. Then when we end up over here and we start to backtrack that way, we can ask, have we been there yet? By checking, are we within some radius of that point? And if we do that, then all of these arrows are going to essentially only grow outward, and they'll eventually get to the goal, and eventually we'll have a path from the start to the goal, and we'll have solved the problem. Do you agree? Now, if we didn't make our radius the right size, we might get a little bit of backtracking, but eventually it'll fill up with space. Yeah.
So what happens if you get kind of like caught in a corner, so to speak, as it's searching out a path?
Okay.
You would.
So we
Still have other branches.
We get to here, and there's all these circles blocking us off.
Right.
We can't find any direction that gets around that. So there's nothing left to do.
That can't be an optimal path.
Well, yeah, it can't be an optimal path, so I'm perfectly fine with that path wasting its time because somebody else is going to find the goal. That's essentially my statement. Surely no optimal path does this type of thing. You're coming around here, move down, go around here. Oh no, I'm stuck. I boxed myself in, right? I mean, so therefore, some other path's gonna get out of there first. Just okay. I can't remember why I started with continuous space. This is actually much more intuitive in discrete space, but I decided to start with continuous space anyway. Let's go to discrete space now.
Isn't that just like kind of like dynamic programming?
Yeah, that's exactly what it is. It's just remember where you've been and don't go there again. Okay, in this case, there's 4 directions. In each spot, you're going to go left, right, up, down. You're going to try all the combinations. Now, does it matter what order we do this in? Let me add a few more. So let's suppose I implement this recursively. What's recursive going to do? That's going to do a depth first search. You know the difference between depth first search and breadth first search, right? So here's a depth first type of thing. We're going to start here and we're going to go bing, 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 bing. Oh, that doesn't work. Let's go up. Bing, 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 bing. And if that's the goal, depth first search is just going to get lucky and find it the very first shot. That's awesome. Except what if the goal happens to be right there? Well, now it's going to not try that, then it's going to try all other possible ways. I think by the time it's done, it's going to end up doing something like this. Depending on the order in which you visit all the different spots, it's going to do something really bad. It'll eventually find the goal. As soon as it finds the goal, we have a terrible solution, which is kind of dumb. But as long as we keep on going, oh no, my undo buffer ran out. I have to go fill these in. We'll just pretend there's a border in this game. Okay. What I'm saying is you don't want depth first search. You see why, right? Depth first search is bad. Breadth first search, however, is awesome. If you're here and you want to go there, and you're doing breadth first search, we're going to kind of go here and then there, and sort of there and there. And our frontier is expanding in this breadth first manner, and the very moment something reaches the goal, we know we found the optimal path. By the way, this wasn't a single search path, this was a whole bunch of search paths in parallel, which differs from what I was doing a moment ago with depth first search. Did you catch that? Okay. How do you code that up? Your job is to implement breadth first search. What do you do? Can't use recursion because that would do depth first search. Surely you've studied this before, right? Somebody knows the answer, just tell me. Use a queue. Okay. Here's what your code looks like, essentially. So we'll say q equals new q. Q dot push start, where start is the starting point. While q dot size is more than 0. Then we'll say current equals q dot pop. And then for each neighbor of cur, q dot push may. There, breadth first search. Start goes in, start comes out. All of start's neighbors go in. All the neighbors come, as we keep going through this loop, each of the neighbors comes out and all their neighbors go in, and this searches the whole space. Except I made a huge, huge mistake, which I covered earlier. What was my mistake, and how do I fix it?
Keep track of where you've been.
I'm not keeping track of where I've been. So what kind of structure do you want to use now?
Just
I heard tree list.
Tree set.
Tree set?
Point plus.
We'll use some kind of a set. S equals new set. Okay, let's see. How about if S dot contains cur, then continue, meaning never mind about the next thing, and then here S dot add cur. Kind of did it, right? There's some kind of a set, probably a tree set or a hash set or some kind of set, and everywhere I've gone, it remembers, gonna go everywhere until I reach the goal. Okay? How would we do this in continuous space? Suppose we're doing this fuzzy continuous thing where we've got a radius around all of our endpoints. What goes in the set? Or how are you gonna do a set? It's not gonna be easy. Basically, every time you want to check if S contains something, you're probably gonna have to run through the whole set and check if you're within some radius of every single thing in the set. If you really wanted to do that, there's a nice data structure called a vol tree or a KD tree. Anybody heard of any of those? Turns out those are data structures that are really good at finding if you're within a radius of some point in a whole set of points in continuous space. So if you need to do this, vol tree, KD tree, any of those will do it. They exist. I'm not planning to teach them this semester. I teach them in another semester. But moving on. Okay. I think this is going to accomplish breadth first search. It's going to find the goal. And once it gets there, great. But now there's a problem. So what? How do we... whole bunch of different paths have gone out in parallel in all these different directions, and one of them reached the goal. At that point, we declare success, and somebody says, okay, what was the optimal solution? How do you get it? So here's our code. Give me the optimal solution now. I guess we better have a, where are we going to put this? If cur equals goal, and now what I want to do is print the path from the start to the next step to the next step to the next step. Somebody help me get that out of here.
You gotta trace up the parent that you might have been keeping track of.
Yeah, so we've got these objects of unspecified type here, called cur. And every time you push your neighbors here, we're going to say for each neighbor of cur, we're going to get all your neighbors and push them into the queue. Imagine that this type has an extra pointer for a linked list in it. Right? You can do that. You can just add a next pointer or a prev pointer or something like that. And every time you get one of its neighbors, you tell that neighbor, nay, that its previous one is cur. So I'm going to do that right here. We'll say, and yes, I know I'm writing code that will never compile. But that's okay. I'm going to say nay.prev equals cur. Now, as I'm branching out, I'm essentially doing the same thing I did in this case, right? Where I've got all these arrows, and these arrows form this kind of continuous line all the way back to the start. So as soon as I find the goal, suppose the goal is found by some object, some node, I can just get the prev and the prev and its prev and its prev and follow it all the way back until I get back to the start. And behold, I now have a path that goes from the start to the goal, and it is the optimal, guaranteed optimal path from the start to the goal, or rather from the goal to the start. How do I turn it around? That's an implementation detail, that's your problem. I just teach theory. Okay. You can use a stack, you can push them all into the stack and then pop them off the stack. You can, I don't know, however you want to do it. You can make a doubly linked list, and then you can run it both ways. You can, I don't care.